Okay, so the next thing that we have here is called the algebra of events. And let's see how we can basically do some operations on these events. So algebra of events. So basically it says that in the chapter on sets we have studied about different ways of combining two or more sets, that is union, intersection, difference, complement of a set, etc. Of course we haven't, I don't think I have done that sort of thing here on YouTube, but I have gone through those chapters before. And but it's not really that complicated to do those operations on sets, meaning that there is only these are the different ways of basically combining two or more sets. Combining two or more sets. Which is basically the union. There is the union, there is the intersection, there is the difference, the complement. I don't remember what the complement was. Difference and the complement. If it's necessary, I'll go back and do if it's necessary, I'll go back and do a quick review on these different operations. And likewise, we can combine two or more events by using the analogous set notations. Let A, B, and C be events associated with an experiment whose sample space is S. So let A, B, C be events associated with an experiment. A, B, C be events associated with an experiment. And of course, as we discussed before, you know that when we say experiment, we mean random experiment, whose sample space is S. Whose sample space is S. Now, number one, complementary event. Number one, complementary event. Complementary event. Complementary event for every event A. For every event A, there corresponds another event A prime. There corresponds another event A prime called the complementary event to A. Called the complementary event to A. It is also called the event not A. It is also called the event the event not A, which is basically something that we worked with in the previous chapter, in the review that we did. For example, take the experiment of tossing 3 coins. For example, take the experiment of tossing 3 coins. Tossing 3 coins. An associated sample space is S is equal to 3 coins. That would give you basically HHH, then HHT, then you have HTH, then you have THH, then you have HTT, then you have THT, then you have TTH and TTT. Let A be equal to this set, which is HTH, HHT, THH. B, the event only one tail appears. B, the event only one tail appears. So here we have only one tail, and only one tails. And this is tails, of course. Only one tails appears. So clearly for the outcome HTT, the event A has not occurred. So over here we can say that clearly for the outcome HTT, the event A has not occurred. The event A has not occurred. Thus, with every outcome which is not in A, with every outcome which is not in A, we say that not A occurs. This is double quotes occurs. Thus with every outcome which is not in A, we say that not A occurs. Okay. Now, thus the complementary event not A to the event A is the complementary Thus the complementary event not A to A to the event A, you could say to the event A is A prime, which is equal to basically all the elements that you can find in S that you cannot find in A, meaning that for example HTH is already in A, or HHT is already in A, or THH is already in A. So then the rest of these members here, the rest of these members would be in A prime, which you can write them as HHH, and then HTT, and then THT, for example, and then TTH, and then TTT, right? So you have 5 members here: HHH, HTT, THT, TTH, and TTT, which means that you can say that A prime is equal to basically omega, such that omega belongs to S and omega does not belong to A, which is the same thing as S minus A, which is S minus A would be A prime. Okay, so far so good. So the event A or B, the second, now again having the same basically the same situation here, that A, B, C be events associated with an experiment whose sample space is S. Basically, having that in mind, we can say that the second operation that we can, the second part of the algebra of events is called the event A or B. The event A or B. A or B. So let's see what that is. So recall that the union of two sets A and B, denoted by A union B, contains all those elements which are either in A or in B or in both. So you know that basically, recall that the union of two sets A and B denoted by A union B is the set of all elements which are either in A or in B or in both. Right, so we already know this, hopefully. When the sets A and B are two events associated with the sample space, then A union B is the event either A or B or both. This event A union B is also called A or B. So when the sets A and B, when the sets A and B are two events, A and B are two events associated with the sample space, associated with a sample space, then A union B is the event either A or B or both. Is the event either A or B or both. Sorry, this is supposed to be over here. Either A or B or both. This event A union B is also called A or B. Is also called A or B. Okay. Therefore, the event A or B is equal to A union B, which is equal to basically omega, such that omega belongs to A, or omega belongs to B. So that was basically the event A or B. Now there is another type of event which is called the event A and B. Okay, so the next thing that we have here is the event A and B. So the event A and B would be basically about intersection. So the event A and B. So the event A and B, the definition is, we know that the intersection of two sets A and B is the set of those elements which are common to both A and B. So basically we know that the intersection of two sets A and B is the set of those elements which are common to both A and B, common to both A and B. That is, which belong to both A and B. That is, which belong to both A and B. So that's something that we know already. So if A and B are two events, then the set A intersection B then the set A intersection B denotes the event A and B. Denotes the event A and B. A and B. Thus, A intersection B is equal to basically omega, such that omega belongs to A and omega belongs to B. For example, in the experiment of throwing a dice twice, a dice twice, let A be the event score on the first throw is 6. Let A be the event score on the first throw is 6. Score on the first throw is 6. And B is the event, sum of two scores is at least 11. Sum of the two scores is at least 11. Then A is equal to basically 6, 1, 6, 2. So A naturally becomes basically 6, 1, for example, or 6, 2, or 6, 3, or 6, 4, all the way up to 6, 6. 6, 4, 6, 5, all the way up to 6, 6, meaning that we said that A is the event score on the first throw is 6, meaning that you're going to get a 6 on the first throw and then some other number on the second throw. And B is basically 6 and all of these elements, 6, 1 through 6, 5. Right? 11, 6, 6 is at least 11. So it's 6, 5 and 6, 6, I'm sorry. 6, 5 and 6, 6. Right? Now, so then you can say that A intersection B is equal to basically 6, 5 and 6, 5 and 6, 6. And note that the set A intersection B is equal to 6, 5 and 6, 6 may represent the event. So this set may represent the event, the score on the first throw is 6 and the sum of the scores is at least 11. The event, the score on the first throw, is 6 and the sum of the sum of the scores is at least 11. So basically, this set basically it may represent many things, but among all of those things, it may also represent basically this event, which is the score on the first row is 6, and and the sum of the scores is at least 11. So that's that. And then there is one more type of what do you call it? Well, you cannot call it type of algebra, but you can call it basically the way that you combine basically two sets. So there is another way basically that you can combine these events, which is basically the event A but not B. So you have the event, you could have the event A but not B. So you could have this event as well. So let's see what that is. So A but not B, we know that A minus B is the set of all those elements which are in A but not in B. So we know that A minus B is the set of all elements which are in A but not in B. Therefore, the set A minus B may denote the event A but not B. Therefore the set A minus B may denote the event A but not B. So we know that, and I think in the algebra of sets, we had something like A minus B is the same thing as A intersection B prime. I don't know. I'm not sure if you could find this in the part that came with the algebra of sets, but what that means is that A minus B, which is basically A but not B, that is equal to A intersection B prime, meaning that the complement of B and the intersection of A with basically the complement of B. We will test that, we will see how that works. So now let's see, this is actually B prime, which is the complement of B, and you could call this the complement of B. The complement of B, or you can call it also not B. That basically you can call it these two things. But let's see. Let's take a couple of examples. Actually, there is only one example here, and then there is some other material here, and then there is the exercise. So I think we can do all of these in this video, and then okay, so now as an example, let's say that we have let's say that we have considered the experiment of rolling a dice. So you want to consider the experiment of rolling a dice. Let A be the event that, so A, let's take A as the, call it event A, and let this event be getting a prime number. Getting a prime number. And B be the event getting an odd number. So you have an event B as well, and that is getting an odd number. Now write the sets representing the events. So now what you want to do is write the sets representing the events number one A or B, or number two is A and B, and number three A but not B, A but not B, and number four not A. So basically in the experiment of rolling a dice, your what do you call it, this space, I have forgotten the word for that. This whatever that is called, this space would be 1, 2, 3, 4, 5, and 6. And then A is basically, the event A would be, for example, getting a prime number, which would be basically 1 is not a prime number, so you get 2, 3, and 5. These are prime numbers. And event B would be getting an odd number. Odd numbers are basically 1, 3, and 5. 1, 3, and 5. Now, over here, if you want to write the sets, these sets representing these events, for example, A or B would be, we said that basically A or B was basically the situation. A or B was the situation where so we said that basically the union of two sets was, and which was basically A intersection B, the union of two sets, which is basically nothing but A intersection B, for example, contains all the elements that are in A and in B. It contains all the elements that are in A or in B or in both of them. Meaning that either in A or in B or in both of them. So, then when the sets A and B are two events associated with a sample space, that's the word I was looking for. So when the sets A and B are two events associated with the sample space, then A intersection B is the event, either A or B or both. And this event A intersection B is also called A or B. So what that means is that then we said that the event A or B, the event A or B is equal to A intersection B, which is the same thing as basically in raster form it would be omega such that omega belongs to A or omega belongs to B. Now mathematically it's written this way, and if you want to understand it, what is basically A intersection B, so what that means is that, for example, suppose that you have two sets. For example, let's say that A is equal to 1, 2, 3, and you have another set B which is equal to, for example, 3, 4, and 5. Now A intersection B is simply equal to 1, 2, 3, 4, and 5. Okay, and this is A union B. A union B. And A intersection B is just simply the member that they have in common, which is equal to 3. And so this is A intersection B. And A minus B is all the members that you find in A minus the elements that you can find in B. Meaning that 1, 2, 3, and then you have to take away the 3 because they have basically 3, they have it in common, so you have to take it out. You will get 1 and 2. 1 and 2. Meaning that over there previously we said that A minus B is equal to A intersection, I suppose it was something like A intersection B prime. And so, for example, over here, so not B would be, well, we will test this later. Because we need a good example for this, a good situation for it. But basically, that's basically all of these 3 operations in a nutshell. Now let's go and see what we can do over here. So here we said that A or B is just simply A union B, meaning that all the members of A and all the members of B and all the members that they have in common as well, That's A union B, which is the event A or B, right? Which is the event A or B. Now, so what that means is that now let me erase these, and then we can go over here. And so A or B is the same thing as A union B, which is the same thing as, well, 1, 2, 3, and 5. 1, 2, 3, and 5. And A and B would be simply A intersection B, which is simply 2, 3, 5, 1, 3, 5, so that's 3 and 5, the members that they have in common. A but not B would be A minus B, which is equal to, as we said, it was equal to 2. So, of course, that was another example. But A minus B is basically you need to take into consideration all the members of A and all the members of B. So here you have 2, 3, and 5. Here you have 1, 3, and 5. So 3 and 5 they have in common. You have to take it out. You will be left with just the 2. And not A, which is the same thing as A prime. This is not prime, this is just double quotes. So not A is equal to A prime, which is the same thing as 2, 3, 5, 2, 3, and 5. So 1, 4, and 6. 1, 4, and 6. Meaning that you need to go into your sample space, all of these, basically all the members of the sample space that basically take into consideration all the members of the sample space. And not A would be basically all the members of the sample space that all the members of the sample space except for the members that you can find in A. That would be not A. So that would be, for example, 2, 3, and 5. So 2, 3, and 5, you take it out, so you'll be left with 1, 4, and 6. So that's basically, for example, this example here. But in the exercises, hopefully we will get into some situations and some word problems, and then using that we will be able to understand all of these much better. Now there is something called mutually exclusive events. We have had this somewhere before as well. Mutually exclusive events. So mutually, that was in mathematical logic, I suppose. Mutually exclusive events. So mutually exclusive events are, in the experiment of rolling a dice, the sample space is, for example, when you roll a dice, the sample space would be basically 1, 2, 3, 4, 5, and 6. Right? Now consider event A, an odd number appears. Event A, an odd number appears. And B, so event B, an even number appears. An even number appears. Okay. Now clearly the event A excludes the event B and vice versa, meaning that the event A excludes event B and event B excludes event A. In other words, there is no outcome which ensures the occurrence of events A and B simultaneously. So that is basically mentioned. Basically, that is very well said. When we say that the event A excludes the event B, the event A excludes the event B, the event B, and vice versa, and vice versa. Another way of saying the same thing is that there is no outcome. There is no outcome that ensures the occurrence of events A and B, that ensures the occurrence of events A and B simultaneously. So for example here, the event A would be an odd number appears. So A would be basically this event or set. An odd number appears would be basically 1, 3, and 5. 1, 3, and 5. And event B would be an even number appears. So 2, 4, and 6. 2, 4, and 6. So, and of course A intersection B here, A intersection B is the null set. There is no members here that they have in common. That is, A and B are disjoint sets, meaning A and B are in the terminology of sets, they are called disjoint sets. Now, in general, two events A and B are called mutually exclusive events if the occurrence of any one of them excludes the occurrence of the other event. That is, if they cannot occur simultaneously. So then they would be called mutually exclusive events. In this case, the sets A and B are disjoint. Again, in the experiment of rolling a dice, consider the events A, an odd number appears, and event B, a number less than 4, for example, appears. And but now here, basically, we will get to that. I don't want to rush myself. So we have a couple more things here to cover, but before I go any further, I'll take a few minutes rest. Okay, so then we said that the event A excludes the event B, and vice versa, meaning that there is no outcome that ensures the occurrence of events A and B simultaneously. And so, for example, if A is equal to 1, 3, 5 and B is equal to 2, 4, 6, being these two events, then A intersection B is the null set, meaning that A and B are basically disjoint sets, meaning they have nothing in common. And where were we? So in general, so then we say that in general, two events A and B are called mutually exclusive. Two events A and B are called mutually exclusive events if the occurrence of any one of them excludes the occurrence of the other event. If the occurrence of any one of them excludes the occurrence of the other one. The occurrence of the other one. Of the other basically event. That is, if they cannot occur simultaneously. That is, if they cannot basically occur simultaneously. In this case, the sets A and B are disjoint, meaning that, of course, if the two sets are disjoint, then they're mutually exclusive. And again, in the experiment of rolling a dice, rolling a dice, consider the event A. Which is an odd number appears. And the event B, which is a number less than 4 appears. Now A is basically an odd number would be, for example, when you roll a dice, basically your S would be equal to 1, 2, 3, 4, 5, and 6. And so an odd number would be 1, 3, and 5. And a number less than 4 appears would be, for example, 1, 2, 3. That would be B. So now 3 belongs to, you know that 3 here belongs to A, as well as 3 belongs to B. Therefore, A and B are not mutually exclusive events. Therefore, A and B are not mutually exclusive events. And simple events of a sample space are always mutually exclusive. As a remark, you can say that simple events of a sample space are always mutually exclusive. And there is something else about exhaustive events. And then we have a couple of examples which we will do in the next video. So I'll see you in the next video.